All right, so let's see what this new matrix M looks like in numbers, numerically. So this would be P inverse. Well, let's see, P inverse is 1 over 5. And then I'll have swap, negate. All right? That matrix transforms us from E to B. So it's going to go like that. Then I've got matrix A. 1, 4, -2, 5, EE. And then P is going to be 2, -1, -1, 3. EB. And you can see how the indices work along the subscript. We go BE, EE, EB. So the output of this multiplication is going to give us a matrix that transforms R2B to R2B. All right? So let's see what we've got here. 1/5. I guess I can stick with yellow. Well, yeah, I'll stick with yellow until I do the multiplication. We'll do that. 1/5. And then it's just going to be 3, 1, 1, 2, BE. Here I'm going to do the multiplication. So I'm going to have an intermediate color, which shouldn't really be green, but I have green. All right, so let's see what we've got. 2 plus 2 is 4. And then we got -1 minus 6 is -7. Then I've got 8 minus 5 is 3. Then I've got -1 plus 15, or sorry, -4 plus 15 is 11. If I did that correctly. All right? And so now I need to finish the multiplication. And this is going to be fully orange. So let's see, we got 12 and 3 more is 15. Then we got 4 and 6 more is 10. Then we've got -21 plus 11 is -10, I think. And then we've got -7 plus 22 is 15. And this should be B. All right? And so what does equal? We can cancel out a 5, and I'll get 3, -2, 2, 3. And this is B, B. All right? We can't expect that that overall factor of 1/5 will always cancel out. That was actually an accident here. And I hope it doesn't mean that I made a mistake. But we'll check and see what happens just by verifying that it does the same thing in the B basis as it does in the E basis, as A does in the E basis. Well, we have two vectors here. So let's see what happens to AX. All right, well, this is going to be all right, so I've got 1 minus 24, 4 plus 60. All right? So that is the action of matrix A in the E basis. Let's see what happens in the B basis. All right, I've got 3, 5. So that's going to be 9 minus 10. All right, and then 6 plus 15. Negative 1, 21 in the B basis. Now, the moment of truth, we'll be seeing if these two vectors are simply different representations of the same vector. So let's see if they are. I'll have negative 1 times 2, negative 1, right? Plus 21 times negative 1, 3. And let's see what that gives. These are both E. Negative 2 minus 21 is negative 23, and 1 plus 63 is 64. So it seems from this example that matrix M does indeed do exactly the same thing as matrix A does, just with respect to a different basis. That would be very strange. These two matrices don't look the same. I mean, I guess this component's the same, but I'm going to let you know that's an accident. So, does that mean that every matrix is the same as every other matrix? Well, no. No, it doesn't. Because this relationship between matrix M and matrix A is very, very, very special. Now, that's not to say that there aren't an infinite number of matrices that are related to A in this way, just with respect to different bases. There are. There are certainly an infinite number of matrices that are related to A in this way. But that doesn't mean every matrix is related to A in this way. This relationship is called a similarity transformation. And every matrix M that is equal to the inverse of a matrix times matrix A times that matrix again is said to be similar to matrix A. All right? So I was saying that not all matrices are similar to matrix A. One way to see that is to recognize that certain characteristics of matrix A are invariant under a similarity transformation. All right, so while matrix A and matrix M certainly do not look the same, there are characteristics of these two matrices that must be the same, precisely because they are similar matrices. All right?